In this video, we'll work out a slightly more advanced related rates problem example, one that involves water flowing into a tank that is shaped like a cone. We have water flowing into a conical tank, a tank shaped like a cone with the point downward, with a radius of 5 inches and a height of 8 inches, and we know how fast the water is flowing in at 6 cubic inches per minute. Our problem asks us how fast is the height of the water in the tank increasing when the height is 3 inches. So our key points here, we're trying to connect the height of the water in the tank to the volume of water in there. So as always, let's start by drawing a picture to see what we were looking at here. Here we have our tank. It is a cone with radius 5 inches and height 8 inches pointed downward, and our water is flowing wherever water is sitting at the bottom of the tank. So we have H here, which is the height of the water in the tank, and I want to connect that to the volume of water that's in the tank right now. Well, if I assume this is flat, this here is also a cone of some radius and some height. Now for a cone, the volume of a cone is always 1/3 base times height. In this case, because our base is a circle, we know that area is going to be pi r squared. This will be 1/3 pi r squared h. Seems simple enough, we get to differentiate this thing and go for it. However, the issue is that the radius also changes with height. If the water is way up here instead, then we have a larger radius. And so radius depends on height, which therefore will also change in time. So we can't just directly differentiate and get dH dt and go from there. There's a little more work here first. And the way that this is usually dealt with in this particular case is I want to figure out how r depends on h, and then just use that to write my entire equation to be only in terms of h, and that will get me to something where I can differentiate and solve it out. So our main question here becomes, how does r depend on h? Or how do r and h relate? And this is the reason why this problem is more complex and more challenging. The way we want to think about this problem is to take a slice through the middle of this cone. Take a vertical slice straight down through the cone. What I get is a triangle. And I'll put this red line here to indicate the water level. Now if I drop a perpendicular from the middle all the way through the peak, assuming that line is straight, what I know is that this half side here is 5 inches, and the entire height here is 8 inches. And furthermore, because this is a right cone and all of these things are right angles, the two triangles on the right half of the picture here are similar. The big triangle that goes all the way from the top of the cone all the way to the bottom, and the small one that goes from the bottom only up to the water level. Those two triangles are similar, and this distance here is r, and this small distance here is h. So by using similar triangles, we can see that r over 5 equals h over 8, because that's pairing up the same sides of the same parts of the triangle. And so r equals 5/8 times h. That gives us our connection between r and h that we can use to set up this problem. We're going to plug that into our volume equation way up at the top. We discovered before that the volume of the cone, which is the volume of the water in the tank at this point, is 1/3 pi r squared h, but r is just 5/8 h. 1/3 pi 5/8 h squared times h. Or simplifying out, I will see a 25 on top, a 64 times 3, or a 192 on the bottom, pi h cubed. And now with this, we can actually differentiate and solve it out the way we need to, because the things here that change in time are just v and h. I really have v of t, 25 over 192 pi h of t cubed. I can differentiate everything here in t to get that dv dt equals 25 over 192 pi 3h squared dh t. 192 was just 3 times 64. So this becomes a 25 over 64 pi h squared dh dt, which means that we can solve for dh dt as 64 over 25 dv dt divided by pi h squared. Now if we go back to our problem statement, we want to know how fast the height was increasing when the height was 3 inches. So we know height is 3. We're given dv dt is 6. And we can plug everything in. When the height is 3 inches, dh over dt is 64 over 25 times 6 inches cubed per second. That was our given dv dt over pi times 3 inches squared. I can cancel one of those with a 3 on the top. So I'm left with 128 divided by 75 pi inches per second will be the rate of change of the height in this scenario. So there is a more involved related radius problem. We have to use multiple steps to get the right volume you need and then figure out the radius so that you can figure out how fast the height changes with time in this given scenario.